you can see many years graduate degree. So I received my PhD degree in the University of Texas El Paso in 2022. Okay, 2022. And I did my postdoc New Mexico Tech for 2 years. Then I came to University of Texas San Antonio as assistant professor and associate professor. So I was the funding director for the NASA Center for Extreme Research for Advanced Measurement in Extreme Environment, UTSA, and I also was the department chair. Please, yes. So we just started. Maybe you this time also you can introduce yourself. My name is Romina. Romina. Okay. So which department? Which department?
Department of Geography.
Oh, department of oh here. Okay.
Yeah.
So you graduate student?
I am
Master. Yeah, she's master.
Oh, master's. Okay. Yeah. Okay. So my specialty is water, cryosphere, climate science using remote sensing, geospatial science, analytical, machine learning, deep learning, and modeling. Then my research area is very broad. So I help be in the Antarctica, Arctic, Tibet Plateau, and the Rockies, the Andes, a few times here, the Moon and the Mars. I didn't go to the Moon and the Mars, but I have lots of satellite images you can use to do the research. And I think there's a lot big effort right now in NASA in USA and the European Space Agency go to the Moon and go to Mars. Lots of investigation, lots of emphasis, and that's why our department was geological science and we changed the name to Earth and Planetary Sciences. So that's one strategy for us to move to this direction to study the planetary science. So I have published a lot of papers. So if you're interested to look at my papers, remote sensing cryosphere study. So you can go to Google Scholar and to see my publication. So published over 150 papers, collaborating with lots of people. So I think today we will talk about the altimetry, radar, laser altimetry. There are two different types of altimetry. One is radar, one is laser. So I don't know. Everybody, well, I know somebody already know what it is, but I want to ask, yeah, you have listened, what is the altimetry? What the radar? What the difference between radar and laser or lidar altimetry? What is it? What is it? Maybe is anybody want to?
Difference between radar, radar is light, and radar is like magnetic.
So lidar and radar also pulse actually electromagnetic. Yeah. So they're pulse. Okay, that's good. So what's the difference? What is the difference between them? Huh? Oh, okay. One can pass through the cloud, one cannot. That's a good point. So radar actually can pass through the cloud. Lidar cannot. Okay. So means radar is actually much longer wavelength and pass through the cloud. So radar is in the microwave. Lidar is in the visible or the infrared. So much short. Nanometer. So radar is in the microwave. Okay. So altimetry, what do we mean? Altimetry. What do we mean? the elevation, the altitude. Yeah. So altimetry means radar, LiDAR, they can measure the elevation very same. Okay, so this is important. So we are talking about this type of sensor. It can measure the elevation of the surface. So if your surface does not change, then your elevation will always the same once they pass through. But if they change, then you will see different elevation. Then you will see how much change. For example, the water level, how much change. The ice, how much melt, or the earthquake, if they change, how they shift. So that is the application of the altimetry. You can build a digital elevation model, and also study the change of the object. Okay. So we use this to study the sea ice change, the glacier change, the ice sheet change, the water level change. Lots of application. We can also use this to study the canopy height. The canopy height. Because we measure the elevation, right? We can measure the surface elevation. We can measure the canopy, the top of the tree elevation. Then we can measure the height of this canopy. And then we can even measure the biomass of the canopy. Okay, so this is all of this type of application based on the elevation, the altimetry characteristic to measure the elevation. Okay, so radar a lot. So that's the big difference. So if we look at this figure, so the radar actually, you see, I think the students say that the radar actually can penetrate the cloud in the right, penetrate the cloud and get to the surface. And the LiDAR you see on the top, this LiDAR point is not penetrate, does not penetrate, okay? But they can penetrate the if it's a very thin cloud, they can pass through. But it's a thin cloud, this will not pass through, okay? And but the radar can pass through thin cloud. And if this is the sea surface or the land surface, they will directly get the elevation from the surface of the sea, the surface of the land. But if the surface is snow or ice, what is the difference? So the LiDAR will get the surface of the snow, but the radar actually can penetrate into the snow, get to the interface between the snow and ice, and see this is the one actually completely pass through the snow, get to the interface of the snow and ice. But this one is in between. So it's not exactly pass through the entire snow cover. Okay, so that is the difference between radar altimetry and LiDAR altimetry. And of course, if we do the sea ice, we mostly interested this parameter called freeboard. This is a very important parameter for our sea ice study, but it's not that important for any other study. Okay, so we call it freeboard. But I'm not going to go detail because I'm not focused on the sea ice today. But that is a very important parameter. We actually use that to derive the freeboard. Then we can derive the thickness of the sea ice. Okay. So that's a little bit different between radar and the LiDAR. So we talk about the wavelength. Radar, the wavelength is microwave. Usually like if it's a C-band, we have the C-band, L-band, P-band. Okay, C-band is like 6 centimeters, L-band is like 20 centimeters, P-band is like 60 centimeters. So the wavelength will be long. But but the LiDAR usually is visible. Visible is from 400 nanometer to 700 nanometer. That is visible, and near infrared is 1,000 to 2,000 nanometers, something like that. Okay. So our focus today is on the laser, which is visible and the near infrared. Okay. So there's two LiDAR systems in Earth right now. Very important is NASA LiDAR system, one called ICESAT, one called ICESAT-2. ICESAT-2. Is anybody use ICESAT or ICESAT-2 here? Nobody yet used yet. So yeah. Okay. So my research actually we used all of this data from the beginning. ICESAT started 2003. So we started using the data 2003. ICESAT data start 2003, finished 2009. Then ICESAT-2 started 2018. Okay, so this is the new generation of ICESAT. They both launched by NASA. Okay, so ESA actually have the radar altimeter. ESA, which is the European Space Agency, they do lots of radar altimeter. But NASA is more focused on the LiDAR altimeter. So this is the 2003-2009, which is the old ICESAT. Then 2018 is the new ICESAT. They are very much improved, from the ICESAT to ICESAT-2. Okay, lots of improvement. So I will talk a little bit about this two satellites. So ICESAT, the 2003 to 2009, which have two laser wavelengths. We say two wavelengths. One is the 533 nanometer in the green band, right? Green band. Another one is a near infrared, 1064 nanometer. So they use these two laser to study. So you can see this is the laser point coming down from the satellite. Okay, hit to the surface and return back. They measure the time and they measure the distance. Okay, because we know the travel speed of the light. If we know the time going down, come back, then we know the elevation. So this elevation actually is very accurate. For flat surface, the measurement of the LiDAR elevation is 2 centimeters. 2 centimeters, very high. Surface, the elevation air can be up to 10 centimeters. So there's 10 centimeters air. But if it's flat surface, only 2 centimeters. Only 2 centimeters. Okay. So I'm not going to go too detailed about this. So just remember, ICESAT, even though there's two lasers, 1064, 532 nanometer. So these two wavelengths, but they use the 1064 nanometer for the land surface, use the 532 nanometer for the cloud height, measurement. Okay. The difference between ICESAT-2, actually, ICESAT-2 only uses one laser, which is use the 532 nanometer. So ICESAT-2 only uses the 532 nanometer laser and measure the land surface, and also can measure the cloud. If the cloud is thick enough, so the light will not pass through. So we can also use that 532 to measure the cloud height. So here, of course, there's a mention about the laser. You come to the surface. What is the footprint of each laser point on the ground? Okay, so you can see here we say 70 meter. Okay, 70 meter, which is a laser footprint on the ground, and because when the satellite moving, each laser shot will have a space in between. So in this case, the space between two laser shots is 170 meters. 170 meters. Okay. So this is an example. So this will show you each footprint is 70 meters, and the distance between the two footprints is 170 meters. So that is the ICESAT. So if you have a thick cloud, in this case, cloud, they can measure the cloud height. So ICESAT-2 is a new satellite. They launched, I think, they mentioned in 2018, and it only used the 532 nanometer. Only used the 532 nanometer beam, and the footprint is 11 meters. 11 meters compared to the ICESAT. We say that how much that? 70 meters, right? 70 meters. Okay, so this is a big difference. The footprint is much smaller, means you can get a much higher accurate elevation for specific points. Okay, and also the interval between the two footprints, we say the ICESAT is 170 meters, right? But here the footprint between each two footprint is 77. So means all of these footprints almost overlap. There's lots of overlap. Okay, not like ICESAT. So the distance between two footprints 170 meters. This one is 77 meters. So you have lots of overlap. Okay, so that is the difference. Another big difference is ICESAT only have one shot, one track. But ICESAT-2, there's 6 track. One times 6 beam, 6 track. And this 6 beam is separated into 3 pair. 3 pair. Okay. So each pair we have 2. We have the left and the right. We call it weak and strong. So there's a weak beam, strong beam, weak beam, strong beam, weak beam, strong beam. So 6 beam. Okay. And the pair between each pair is 3 kilometers. Between each pair is 3 kilometers. And in between the pair, the distance is 90 meters. 90 meters. Okay. So you can see this is 90 meters in between the left and the right. 90 meters. And between the 2 pairs is 3 kilometers. Okay. And each footprint is 11 meters. And in the space between each 2 footprints is 77. So you can see how big improvement is ICESAT-2 compared to ICESAT. Okay. So far, any questions? Okay.
With the clouds, I didn't totally understand. So, with one signal penetrate through the clouds and get 2 signals back, or you just get the cloud signal back?
So they send the 6 beam 6 feet up. Out of the surface, there's lots of photons. They count the photon, but the difference between the ICESAT-2 is also the ICESAT-2 is a photon counting. So there's lots of photons. They connect the number of photons, but you only have there's thousands of photons. Even the light also has the 332 nanometer photon go to the surface, and some of them also return to the sensor, but they will only. That's lots of noise actually. So this noise will be removed from the pre-processing.
So I said 2, you have the possibility to get maybe 2 signals if the cloud coverage is big enough.
You actually can get more than 2. I think they usually get more than 10 signals. If there's no cloud, yeah, they always see cloud.
So you have kind of different layers where you see the fragments.
Because they have lots of signals coming. Here is the ground, they can return a lot. Here's the ground, they have a little bit of reflector to different direction. But and also depths. Even in the one location, they have different depths, right? But they eventually average that 10 photon back to the average is into one elevation. So each photon will get an elevation, but the product, we will talk about the product. The product they have, they aggregate different photons into one average.
So in the post processing, you have to kind of remove the canopy height, the clouds and everything, but you're just interested.
Oh yeah. There's lots of algorithms involved with the pre-process into the product.
What is the partial coverage? The ICESAT-2 from the 4 to 4?
Oh yeah, good question. Yeah, it's not those cells. So cover the entire Earth, but is more dense in the polar region and more sparse in the greater lower latitude region. We actually look at even these glacier. We don't get many tracks on this glacier. Yeah, it's not too far from here, and it's not too far from the Antarctica, but it's still really sparse. Yeah, the track is really sparse. We actually will look at the tracks today. Any other questions? So this is an example. Also show you you have the 6B. You have 3 pair. Each pair you have left, right. So the left, usually the left one is strong B. The right one is a weak B. So the strong B, the energy actually is 4 times of the weak B, 4 times stronger energy than the weak B, and then you get in the same time you got this 6 B information. In this case, it's actually the sea ice. So you can see the higher sea ice go to the sea level, higher sea ice go to the sea level, higher sea ice go to the sea level. Then you have lots of open water. Yeah. So you can see there's then you have the strong B, the left, weak B, the right. Okay. So this is the center of the track, and then you have the strong B in the left, weak B in the right, strong B, weak B, strong B, weak B. Okay. So we usually call the being yeah. So this is the being we call the 3, we call the 2, we call the 1. So it's 1 left, being 1. If you look at this one, okay. So this is a being 1, we have left and right. You have B, this is B2, left and right. Then you have B3, left and right. Of B1, B2, B3, B4, B5, B6, which is the 6B. Then if we talk about the pair, is pair 1, pair 2, pair 3. Okay, pair 1, left, right. Pair 2, left, right. Pair 3, left and right. Or B1, B2, B3, B4, B5, B6. Okay, so that is the information, lots of data. Okay, so here I have a few videos. Then we can go to some demo. So because today I think this is the most lecture part. I will go, but I will not do much of this part. Then most practical. Okay. So let's do the video. Let's see if we can open that. So I say, as Alfonso told, when I do the video, I need to stop that sharing, right? Then we share that. We share this video. Is right? Let me do that. How share this video. Yeah, so you can send. Yeah, we have the link is yeah, the link is in the PPT. So if you open the PPT, if you like it, the link is in the PPT. Yeah. So for example, yeah. So this is the if you like, right? Yeah, you see the link. So they didn't get that the link from Alfonso. He sent the link. But I think
¿Pudieron abrir el link que le mandé conmigo?
Cuando la gente es joven,
yeah. Yeah. So I said, yeah, the PPT. Yeah. Okay, so this is the link, the data. Let's put it to the Zoom. Yeah. Is I don't know if you guys can see that. No? Right. Copy the select. Copy the link. Copy the link. Okay. Then Yes, yes. Okay, so this one should.
I don't see it in the office.
Okay, yeah, so I think because I'm going to, because there's some need, some video, I need to.
Chair, you have to chair the,
Yeah.
yeah, so you have to chair that application.
So
Then you get into,
yeah, so this is big.
yeah, no problem. Speak there. And I have to open the Zoom. Let's just share screen and share that.
Yeah. So that.
Yeah. And just do it play.
Yeah, so let me go back.
Yeah.
Yeah. So this is, you can see that each time say the 6 beans. 3 pair. So yeah, 2 zeros. There's quite a few of this video. I can go through each one.
Exercise. Place your hand in your phone right now. Come on, let's just do this.
Oh my God.
Now, look at those.
Okay. So is there any way I can directly copy the other one?
Para que no lo tengan. Si no está en la presentación.
Pero el video,
El PPT,
el video no está porque el video tiene que estar en la
Okay, so this is the other one.
Pero
The P.
sobre el video.
Oh, el enlace. Yeah, the other. There's another one.
Okay.
There's another one.
I'm opening.
Right, yeah. So it's also in the Okay, so this is the second one. Is that we can directly open from here?
No, you should share the,
Yeah.
open it and then share the screen. Right. And now you share that screen. Share the screen. And share that.
This show the video.
Now you can.
So I think probably this all of this video will be shown quickly at the same time. There's quite a few small videos showing the
300 trillion. That's about how many photons it sounds like a lot, but as the photons sail through the atmosphere and bounce off the Earth, they reflect back, just like anything in all directions. Atlas receives only the photons that reflect straight back to the instrument, just about a dozen photons.
Yeah.
That minimum of photon received must be very small in order to keep the timing error of those photons very small, which allows scientists to calculate elevation very precisely.
Yeah, so this is we have some others. Stop here and share another one. I'm sorry for, but yeah, this is the other one. Let me see. I think maybe we don't need to show all of this. You guys can. Opening. Okay, then this is the second one. Then share. So this is one.
532 nanometers. That's the wavelength of a bright green color, the color of the Atlas lasers measuring the elevation of the Earth below. When Atlas receives photons back from Earth, it has to
It works.
that naturally reflects off the Earth, which would overwhelm the detectors. So Atlas only lets in light that is exactly 532 nanometers. Sunlight in that wavelength range will also set off Atlas detectors. And so computer programs are needed to filter out those sunlight photons in the data.
So this is another one. Let me show there's one more. So once we finish, I think we are good. This is the other one. Let's copy the link. This is all very short. Let's see. Shit. Oh, this way can actually show the original sound. Okay.
90 meters, the distance between each laser pair. In order to measure the slope across the laser's path in a single pass of the satellite, Atlas uses 3 pairs of beams spaced 90 meters apart with a reference track between the beams. Then on following passes, even if the 2 beams are slightly upslope or downslope from where they were on the first pass, scientists can still calculate the elevation change of that key track.
Okay, so I think I have one last small video.
Walk through the filtering steps. that
Yeah,
it
this
shows,
is
and there's a
tell you.
data tab, and then click that large /custom order, and that'll actually pull all your filters into Earth Data Search. You don't have to do that twice. So through Earth Data Search, once you walk through that ordering process, you will be presented with an option to customize.
Where's
And
okay. Last one here. Copy the link. The Zoom. Yeah, I promise this is the last one. Let me share. Which one? I think this is the one, right? The last one is this one. Oh no.
(1,387 different orbit paths every 91 days by ICESAT-2). The orbit pattern creates a dense grid over the poles, all anchored here at the Greenland Summit Observatory. Since each orbital path will repeat every 3 months, scientists will be able to observe ice changing between seasons. The more frequent measurements of the polar regions will give us a more detailed look at retreating glaciers, melting ice sheets, and thinning sea ice, and the global impacts of those changes.
Okay, I think I finished all of these videos. We don't have anything else to videos to do that. Okay, so let me close this stuff. Okay, let's go back to the about the product. ICESAT-2 product. Let me go back to share this windows. Zoom. Forward. Here. This one.
¿Sí? Ah, no. Ay, ¿cómo
This
se
one.
llama?
This one.
Minimiza.
this
Sí, minimiza. Y
Project first.
Oh,
Project first. It's gonna be in a kiosk. Small.
okay. This one. Oh, this one here.
And then, yeah,
Others.
so the window should be minimized because, yeah, that's correct.
Oh, but I didn't share yet, right?
No, it's shared, it's shared.
Oh, it's already shared.
It's shared.
Oh, this is already shared.
That's shared.
Oh, okay, good. Sorry. Okay. It's already shared. That's good. Okay, so basically, that videos give you some overview about how the ICESAT-2 works. What's the purpose of ICESAT-2? How many tracks and where is the data connection actually between them? They collect all the data, then distribute to lots of data set. Mostly, I think we will talk about it here. Where to get data.
Not shared again. It's not shared in Zoom.
It's not showing in Zoom.
Ándate aquí a slideshow. Y setup slideshow. Con el individuo. Process. Ok. Comparte. Ahí. O sea, ahí. Y ahora ándate al Zoom.
Zoom.
The stop share. Con el stop share y share again.
Okay.
Y ahora share. Share screen. Esa. Okay.
Okay. Okay. So the first one we will focus our team first developed by University of California in San Diego, British Oceanography Institute. They combined this ITC one now. So first they developed this for ICESAT. ICESAT-2 is also on this OLT, which actually mostly focused on so this one we are actually doing visual look at the six beams and the left right pairs and also see the exact elevation. You got pass through the water, pass through the land, and also if you have vegetation, show you the the vegetation cannot be high, and all of these informations. Okay. So there are the data sets. So there are the open activity as we will go through, which is you can see the result, you can see the data, and it's very convenient for fresh stuff. Okay. But if you really want to do lots of research, focus on area, get all of the data in one time, you need to go to either NASA Earth data set. Earth data, so I have a link there, or go to ICESAT. Okay. So this is a location you can actually select it and get all of the data from the beginning, 2019 or 2018 to current, okay. And all the data, and then they download the data. ICESAT issue. That's those data. Okay. So the altimetry open activity of visualization to directly look at the data, and also for a few data sets you can download it, you can directly download it also, and then you can overlap data with other optical images to see how they change. That's what we actually will do today tomorrow. So I'm not going to go to detail on this data set, but if you're interested, I can show you how to download the data, select the area, and yeah. So then there's another one called ICESAT-2 slide ruler. So if we have time tomorrow, we can also talk about this. Most likely we will not have time to go through. But this one is actually also NASA Garden Space Flight Center. They try to put the data on the cloud. Some of the data are put the data on the cloud, so the people also can directly working on the cloud. You don't need to download data to the local computer, okay? Because the ICESAT data is so big. All three data each one file in like 3 gigabytes. So there's lots of data, big data. So people, if they use lots of data, they from the slide ruler, we don't need to download data. You can directly process from this. Then there's lots of training and how to use the ICESAT-2 data. So one of the very useful training for the ICESAT-2 Hack Week, which is one happening every year, and from hosted by University of Washington. So they actually doing the coming one, 2003 is yeah, this is 2002. The coming 2003 June or May. My student actually attended this academy, so he got lots of information. Most of the material actually I will show today tomorrow will coming from this academy. So they develop this data, these tools, and everybody can use. Everybody can use the open source is answer, and also based on Google's engine, some of them. Okay, so but we will only use data based on Google's engine and directly use the open altimetry data. So directly use answer. So will be very convenient for everybody to get started. But all of the information and material you can easily see. So there's lots of applications. So I'm not going to detail each one of these applications, but I just go through that. Then you know, okay, ICESAT can do lots of stuff. For example, ice glacier. That's the major application for ICESAT is doing. Okay, so you can look at how the ice, the glacier has been changed, and which area has been changed, how much it changed. Okay, so for the Arctic, which Greenland, for Antarctica, and not too far from here, you can see there's lots of area they are melting. So you see the deep red color is melting. The blue color is actually adding some weight, okay, some mass. So overall, these two places are melting a lot. Then ocean sea ice. So ocean sea ice is you can use the I think, let me know if I think let me go back. I think I don't know if I should talk about the different yeah, hold on. Okay, I think I skipped this one. Okay. So this is the different product. Okay, yeah. So the different product, this is really important because NASA, you see, from the beginning, this original data called raw telemetry data, then get to the ATL 01, 02, which is also very low data. So the first really we want to use data is O3 data. The O3 data is the phantom, individual phantom X, Y, Z, latitude, longitude, and elevation. So individual, okay, individual X, Y, so geolocated phantom, geolocated. So if you want to use the original data, that's the O3 data. Don't use the O1, O2 because there's lots of work after that to get the O3 data. Okay, so after that, then based on the O3 data, you can NASA develop all of these different type of data sets. Okay, from O6 to O13. Okay, O6 to O13. So O6 is the land ice height, and then mean surface height around 40 meter segment. Okay, so the land ice height is already aggregate to 40 meter. So originally, each individual phantom is O3, which is 11 meter. But O3 data immediately, which is 11.2 data, is already aggregated to 40 meter segments. So along the track, we have so many points. So the O3 data give you each individual footprint elevation at 11 meters. But the O6 for this land ice is only 40 meters aggregate. So 40 meters, if you have like 10 footprints, they average this 10 as one elevation for this 40 meter segment. Okay, so that's the O6.
Simple mean.
Yeah.
It's just a simple average. It's a weight.
I think they a lot of use they probably use the Gaussian distribution. Yeah.
So you say get it.
Yeah, the peak elevation, the peak point which is that elevation. So use there's different algorithms actually. Different people use it. And NASA one I think is Gaussian distribution. Yeah. So we actually try to also use the O3 data to develop our O7 data. Because O7 data, which is the sea ice high, so the sea ice high is already aggregated 150 phantoms. 150 phantoms sometimes can up to 100, because if there is a clear sky, 150 phantom can be like 10 meters. 10 meters you probably get a really good phantom in 10 meters, 150. But if you have clouds, you actually don't get good sometimes in certain distance. So, but this algorithm, we need to find at least 100, we always need to find 150 photons, then to aggregate as one segment elevation, which the maximum aperture level 400 meters long.
So it has to be like CI species bigger than.
Yeah. So this is the little loss of average for that segment, 400 meters. Originally only 11 meters. So that's what we actually try to do is based on all three data and to get the elevation. And then of course the 10 is the freeboard. I think I mentioned it in one of the slides. I said that most important CI is the freeboard. So this 10 ATL 10 is the freeboard, which is also a product from this CI's high or 7. Okay, so it's so the footprint can be from 20 meters to 400 meters, which is decreased resolution. So what we try to do is try to directly use all three data and use our algorithm to get a much higher. We say we try to like 10 meter average, 10 meter, every 10 meter get a good elevation. So there's also other movements doing develop different algorithms. On the NASA one, the standard one is 150 photon. Okay, for the all 8, which is land vegetation height. Okay, so land under vegetation. So if you have vegetation, you can get the vegetation height, and then you can also get the land height. Then you can get the calorie height, and for the vegetation minus land, you will get the calorie height. Okay. Which is so they already aggregate to 100 meter segments. So this land vegetation height is 100 meter high, surface height. So the OA data we we look at which is the 100 meter, and then the 30 is inland water height. Inland water height, if you have the lakes, the rivers, they actually have the 13, okay, which is the inland water height. Inland water height. I don't remember what is the aggregation. Probably 100 meters also, 100 meter segment. The 12, ATL 12 is the ocean surface height. Ocean surface height. Okay, so that is a major product we use. You can see this is there's another one called in the very right, which is O4. Okay, then the product is O9. Okay, O4, O9, which is actually the atmosphere, the cloud height. Okay. So for people with the atmospheric side, you can use that product O4 and O9, O4, O9. Okay. So that is the atmospheric research. So then NASA is also developing some other high level called the level 3B, level 3B product. So for example, I know there's a ATL 11, 14, 15 based on the all 6. Okay, so it's graded monthly, sometimes graded yearly product. Okay. Yeah. Is there a way that you can calculate this? No. Snow height, yes. Yeah. So that's there's people actually developing that product. But as you know, the elevation, the laser itself only return from the surface. Unless you actually know before snow, you know the surface. Then once you have snow, then you know the surface, then you minus that because of snow depth. So you need you need a data set before the A slope below the surface. And one arm, there's another data set, there's the surface elevation, and you use that one minus the previous before you have snow. And you can get a slope.
So you can use the image from.
Yeah, exactly.
Where I sat from, there's, so for instance, in March.
Yeah,
Before the snow.
yeah, you have, you
Then
can.
you have the surface of the snow and yes.
There's a lot of people doing this, try to develop this product also.
All the student development.
The people develop is not public available research stage. So everybody is doing their own, develop their own method. To do that. So you guys can also do in your area.
I imagine that it's, I don't know, maybe for you, that would be very good, you know, how much oil you're giving.
Yeah.
Yeah, the problem here is because you have bats, you want to use spatial units. So you need to be have some sort of algorithm to relate the changes in elevation in certain path within a much bigger area.
Yeah, because they are so sparse. There are not pass every way. Each pass is only pass they you don't have pass between like a lot of 1 kilometer or 10 kilometers. You don't have much documents.
And that's every 3 months.
Every one is actually will repeat the
It's nearly the same.
But it's not exactly when you look at it.
You need some sort of satellite image where you can allow you to, for instance, interpolate in 2 areas in 2 days, so you have some sort of, you know, because they're just facts.
Yeah.
And we don't, if one photo is not gonna hit the same exact location every 2 months.
Yeah.
Maybe shift it a few meters. So you don't have like a full earth coverage.
They have the fullest covered by the track is really fast.
Right, so you would need like how many plot in order to, like for.
Yeah,
for
that's
instance,
like 1 year.
if you wanted to cover the whole mountain range,
Yeah, for the Arctic, we try to do monthly. Yeah, Arctic impact. For the rest of the area, probably you do a year.
yeah, you have like parallel.
Yeah.
Shift. Yeah, and then the problem is that within a year you. So you see the map there.
Yeah,
Basically.
we're going to see that in the map. That's why the open activity that we are going to see is really powerful. So you can see the data exactly. What they look like.
What do you do the classification?
Classification.
I mean, how do they know, for example, or taking out on 7, where the sea ice and where the exclusion?
Oh, they have the mask. So they have a mask. So in this area, this time, they use this all of the data in this inside this one, they will treat it as rotation sea ice. And
Where do they get the mask?
oh, this is many years of research. Right? We already know. We already know where is the sea ice, where is the glacier, where is
So there is a satellite imagery
Yeah.
classification.
Yeah.
then
the where is the lakes. Yeah.
So you do this for the same day?
Or they're nearly the same day, yes.
Yeah. So they have lots of mask to use.
So the classification is not for the classification.
But depending on the geometry, you can also do, for instance, shifting between water and ice, because this changes in cliffs. Ice, sea ice is really vertical, almost vertical. You can see the different
Yeah.
water and ice.
Yeah.
So it helps you with the interpretation, at least on the sea ice.
So we actually were really interested to directly use the O3 data because O3 data it didn't tell you anything about its land, its calorie, or its ocean, or so you just use the data. Okay, I'm interested in this area. I just download this part of data and I can do my classification. But if you use other product, they only use the mask out stuff. Yeah. But if that year is is outline that the mask you want to give the data. you need to do out the field data.
It's sometimes it can be safer to check the three.
Yeah, but also data is big data. I said one also data, one track, also data is 3 data. But for some people, you are, for example, you are focusing on that small questions or whatever, then you can use also data and then download all the data for that part. You should use the really high resolution. You don't need to use this program. Most data have everything area. You can do this. Okay, so we have already passed through this one. So for example, I said if you want to do a detailed research for long term, you will either use the NASA Earth data or use the ASIDC. I actually really familiar with the ASIDC data. Always I do the snow and ice studies, go to this place to download the data. Very confident, very easy to download all the data. Faster.
In this ATL 03, the bottom also comes with a center uncertainty calculation, or just the average of just the bottom XYZ?
Yeah, just the X, Y,
Not
and
the-
they have the confidence.
Okay,
Yeah, medium confidence, high confidence.
so there's like a
Yeah.
classification of the
Yeah.
bottoms.
Yes, they have. And yeah, I mentioned this one. This one is people because I think the data is so big. People don't want to download data. It's okay, you know. They go to this one slide rule. They actually some of the data is on this cloud, and you can direct program to get data. Actually, my group has can access to the NASA cloud. The NASA cloud is the data is the same in the ASIDC. But ASIDC you download data to local process. The NASA cloud you can directly progress. So my student can bring it to do that. But for regular people, if you don't have the NASA connection, you can go to this spider node. You can. I think I don't think you need a permission to. You just need to log in, register, and should be able to get data. But for the NASA cloud, you need a particular permission to get into that system. Yeah, brands.
So what about Google Earth Engine?
Google Earth Engine, you just need an account.
Yeah, but do that from the data.
They get data. They get data from. So we actually the Google Earth Engine don't have the ICESAT data. ICESAT-2
Oh, they don't have.
Yeah, they don't have. So what we actually will tell you is get data directly from the OpenLT. OpenLT, but OpenLT, like I said, is it show you one track, 2 tracks, 3 tracks. You will not get the full data. So application, I already mentioned that. So oceans, ocean uses the for I'm sorry. Yeah, for the IC glacier is use OH data, or RO6, which is band ice. Yeah, band ice. For this one is 12 with ocean. Sea ice is 07 and 10, and then 21. 21 is graded sea surface high anomaly. Graded sea surface high anomaly. So all of the that is actually probably monthly or yearly product. Yeah. And the ATL10. The ATL10 is graded freeboard high, graded freeboard. 07 is freeboard. ATL10 is graded freeboard. So then 12 is the system high. 90 is the I think the 90 is graded.
It says dynamic ocean.
Oh, dynamic ocean. Okay. Yeah. Anomaly. Okay. Yeah. Okay. So ICESAT-2 can use for lots of other applications related to sea ice, ocean. So might actually do lots of this type of iceberg, glacier lakes, rifting over ice shelf, melt ponds on the sea ice, and ridges over sea ice, barriers, and blowing snow. Okay. So I'm not going to any one of these. So, yeah. Then another application is tree canopy high and the biomass, which basically is all ages, right? All land surface. Yeah, land surface and the vegetation. So you can get this the red one, which is the photo back from the surface, land surface, and the top will be from the canopy. So then you can get the canopy high, use the top minus the land and the canopy high. And so this is the original, you see, from the surface, and then from the canopy. Then you can also calculate the biomass. Use the empirical equation. Yeah, biomass. So there's people actually try to do a biomass product. Okay, so if you're interested, you can look at this. Okay, but symmetry is also a byproduct because ICESAT, the early one, ICESAT, which nobody actually used and try to get the symmetry because we use the 1604 nanometer laser, which cannot penetrate the water. But the 532 actually can penetrate the water, shallow water, up to 30 to 40 meters. 30 to 40 meters. So, yeah, 30 to 40 meters. To get the symmetry of the lakes. But I try to look at the lakes, the water, we see the inflation, but I don't see that from the data set we look at. Okay, so based on time, I don't know how much time this morning we have. Oh, okay. So we can start working on the open activity. So this is a YouTube video. In your spare time, you can go through that. Maybe you can go through that first. Then we can go to the demo. Let's go to this one. Open this. So I see.
Today's feature presentation.
So I need to also.
You're not sharing. So
Yeah. Unshare.
And share that.
Yeah. Stop share.
Yes.
Then share this one.
Pues cuando comparte y si tiene la presentación no representación que tiene la pantalla.
Presentation is called Getting Comfortable with ICESAT-2 Height Data and the Open Altimetry Online Tool. And with us today is Amy Fitzgerald from the User Services team of the National Snow and Ice Data Center, which is also, called NSIDC, that's the acronym, in Boulder, Colorado. And let me tell you why NSIDC, okay? And as you can see here, as you know, ICESAT-2 collects this elevation data from across the planet. Well, this data comes from the satellite. It's downlinked to Earth. As you can see here, it's reformatted, checked for quality, repackaged into scientific data sets, delivered to NSIDC, who then distributes it and archives this ICESAT-2 data because there is a lot of data coming from this satellite. So, NSIDC is great. They worked with us with ICESAT-1 and there's a lot of other missions and campaigns that they work with. So Amy will make you comfortable in looking at this open altimetry online tool by talking about how do you look at the ICESAT-2 height data, how do you look at the globe data and then do some comparisons and find some coincidental overpasses, things like that. So Amy, I will pass it over to you and thank you in advance for this. Oh, I should mention that also at the end we will have a time for some question and answers. So thank you, Amy, and it's all yours.
Thanks, Brian. I'll share my screen here. Alrighty. As Brian mentioned, I work with the National Snow and Ice Data Center in Boulder, Colorado, where it's currently about 40 degrees Fahrenheit, a little over 4 degrees Celsius, and sunny. I'm going to sort of buzz through my introduction to open altimetry and getting around using the data that's archived in this tool. Really quickly, open altimetry is the product of a collaboration between the National Snow and Ice Data Center, the Scripps Institution of Oceanography, and the San Diego Supercomputer Center at UC San Diego. It was a custom-built application to meet discovery, access, and visualization needs of data from NASA's ICESAT and ICESAT-2 missions. Today, I'll be focusing on the ICESAT-2 data and how it relates to data collected for the Trees Around the Globe campaign. Specifically, we'll be honing in more on the ICESAT Atlas Level 3A land and vegetation height dataset, which is also known as ATL-08. So briefly, I'll switch into about the ICESAT-2 mission, as Brian touched on as well. The primary instrument is called the Advanced Topographic Laser Altimeter System, also known as ATLAS, which is a photon counting laser. It's one laser, but it's split into 6 beams. I'll zoom in a little bit here to show you that beam pattern. So it's got 3 weak and strong pairs. You can get a quick glimpse of which are weak and strong by using the Select Beams button here. I'll go over the tools more thoroughly, but just a quick intro to talk to the instrument. Atlas takes measurements every 70 centimeters along the satellite's ground path, and it has a footprint of about 13 meters diameter. The beam pairs are spaced 3.3 kilometers apart, with a distance of 90 meters between each weak and strong beam. So you zoom in a little closer here, you can see the spacing.
Yeah.
ICESAT-2, let's see, repeats its ground tracks every 91 days to allow scientists to track height changes in all 4 seasons. The land and vegetation height dataset, ATL-08, contains a long track heights above the WGS-84 ellipsoid for ground and contains ground and canopy surface information. The ground and canopy surfaces are processed in fixed 100-meter data segments. So what you'll see in open altimetry are the approximate midpoints of the 100-meter data segment, where the terrain and canopy statistics for that segment are reported. So currently, that's what you're looking at here if we, as we zoom around on my screen and are looking at these data points. I'll put a slide up at the end of this webinar with links to the NASA spec sheet for the ICESAT-2 instrument and to NSIDC's gateway for ICESAT-2 data access and the documentation, so that anyone interested in diving more deeply into ICESAT-2, ATL-08, or the other ICESAT-2 datasets archived at NSIDC, you can grab those links and do that. So now I'll introduce the open altimetry web application as a whole. To get going on that, we'll first introduce the reset button. So this resets you back out to sort of your home view. As you can see, there's a calendar option to choose different days of data. we've got a cloud layer button, which is actually the Modis True Color Terra Corrected Reflectance layer. This can be helpful in areas to determine why you might see a ground track, but sometimes the data fall out and aren't available. And one of the primary reasons for seeing a lack of data where you see a ground track is due to cloud cover. The laser doesn't penetrate clouds well. You can also zoom to a bounding box or a point. I'll do a quick demonstration here of zooming to a point. So you punch in your longitude and latitude, click on the update map, and what that's done is actually centered the map to that point. So it doesn't add a graphic. If you want to zoom in, actually, I'm not sure it's centered. Actually, it probably did. I've got the clouds layer on blocking my view. So knowing that it doesn't zoom into that point or add a graphic, but you can then you can manually use the zoom button to get in and know that coordinate, there's a coordinate readout here in the lower left, is about where your cursor is hovering. You can also turn on the reference ground track layer. These, when they're distinct color, are the inactive but present tracks that have data. If I click on one of those tracks, it'll show the dates where data are available. And if I click on that down here in the lower left again, it also updates the map to show what the currently selected date with data are being displayed in the map. I'll turn that off. Over here in the upper right-hand part of the map, you can see that we have a number of different layer options to turn on. Again, I'll focus on ATL08 today, but there's also ATL06, which is our land ice height data set. We have ATL07 and 10, which are sea ice height and sea ice freeboard data sets, and ATL12, which is our ocean elevation data set. We have the ability to change the current map view's projection. So we have the Arctic polar projection, regular geographic, and Antarctic polar projection. There's also an information button, which this goes into detail about the some of the layer details, what comprises the background layers, the data products, a beam legend. And lastly, I'll show the annotation option. If I turn these on, you can see across the map where people have added annotations for points of interest or potentially problems they found in the data. So this is a good reporting tool. If you think you're seeing a data anomaly, you can add an annotation, search it for a small area, and it allows you to change whether you're looking at a data anomaly or if it's an annotation for yourself, a surface feature of interest. So you can sort of dial in annotations, and they'll persist in the map as either public or private, depending on the box you check, to help you get back to where you were. So what I'm going to do here is I've added an annotation that I'm going to search for. I called it globe. So this is where I found an area where we've got ATL08 data that overlie that coincide fairly closely with a citizen science contributed point from the GLOBE advanced data access tool that I found in Sweden. So if I click on my annotation, you can see the details that I added for this. So I'll close that for now. I'm going to open up Google Earth really quickly and just show you. This is where I use Google Earth to plot the coordinates of the citizen science contributed point. So this is, I've just added a screen grab of the line item for this site here. So that's what it looks like plotted in Google Earth. So close that. I'll keep this up for a bit. So that data point lies roughly over here. So it's relatively close to the ATL08 data. If I expand, or if I click on one of these points, I can get the snapshot of the latitude, longitude, and the elevation at this point. What you may notice is there's a couple of things going on. As I mentioned earlier, the ATL08 data are being reported as aggregated data over a 100-meter segment. So this point isn't necessarily really the exact height of a tree in this area, but it is, if we were in an area with sort of a continuous forest, it would be the continuous height approximately over that 100-meter segment. And so I'm having to make some assumptions that in this neighborhood, the tree heights are possibly similar across this subdivision if they were planted at the same time, and should reasonably reflect what this citizen science collected at the point that's over here. But it isn't an exact art, and it's the best we have for the time being. The ATL03, which is the geolocated photon data, is the underlying data, and I can show you that in a little bit. That is unclassified, whereas the ATL08 has been classified into canopy height and terrain elevation. And so the background noise and errant photons have been cleaned out to report just the data and other important parameters that you would potentially be interested in. So another thing that you might notice is that this elevation for the satellite data of ATL08 is reported at 73.9 meters, whereas the citizen scientists have reported that the elevation at this site was 37.6 meters. And this is because Atlas is reported in as a measurement reference to the WGS-84 ellipsoid height, whereas the terrain height being reported from the Globes app appears to be what's called orthometric height, which is sort of your land height in the area where you are relative to sea level. So I've got a quick graphic that I'll show. It's a brief explanation of why we're seeing a difference in elevation, but there's also, I've got a geoid height calculator that you can use to run through the routine of showing whether you're on track or not. What I've done is used, let me show you that really quickly. It's the UNAVCO GeoHeight calculator. This is one of the links I'll include at the end of my presentation. It lets you punch in the latitude and the longitude and the GPS elevation. So these are going to be the coordinates from the ATL08 data. When I submit this, it spits out what my the GPS ellipsoidal height is. We knew that was the elevation I input, and it calculates the geoid height at 36.7 meters. Orthometric height is calculated by subtracting the geoid height from the GPS ellipsoid height. So this 37.25 meters is the approximate orthometric height in this area, which again goes back to my diagram here of how it actually matches reasonably well with what the citizen scientist had measured. The canopy heights in ATL08 are reported as a difference between the canopy photon height and the estimated terrain surface. So you don't have to worry about any conversion in the tree height reported here. Over this 100-meter segment, the tree height was calculated to be about 4.5 meters, which it coincides roughly with the tree height calculated, but it won't be exact because this person calculated the exact height of a very specific tree that isn't directly in line with the ATL08 orbit track. Well, the ICESAT-2 orbit track collecting ATL08 data. So another functionality that you have within open altimetry is, I'm going to scooch this over a little bit. If I use the select a region tool, and this allows me to view the elevation profile over this area. And so this is what you also saw. I kind of cheated and gave you a preview in my geoid height calculation summary. But you can see how on the map over here, the blue dot is highlighted as I move my cursor along the graph of the weak and the strong beams over here. So this is just the surface elevation area being reported, and then the canopy heights are reported in the graph below here for all these points. And not every point qualifies to necessarily return a canopy height. There are restrictions in terms of the number of photons that need to be received and but in the processing of the data before a canopy height can be generated. So you will sometimes see a little data gap. And this is where if I switch to the ATL03 photon heights, you can see the data returned here. But again, these are high confidence, but we still don't have a classification to know whether these are necessarily backscatter or noise. We can't tell whether this is a canopy versus the terrain. And that's what ATL03 has done the extensive processing to classify and give us a relative confidence of what we're looking at for any given beam. So lastly, I'll touch on how to get the data. If you click this download data as a CSV, that will do a quick download of all the data, again, located just within the select a region. So it's subsetted to be the data contained within this area. And if you choose, excuse me, the second option is to download the data subsetted in HDF5 format. And that will be delivered from NSIDC to you to use as you choose. Lastly, there are some options within these little hamburger icon to fiddle with your chart view. You can download a PNG image or other images of this exact chart in different formats. That's about it for my presentation. Like I say, that was kind of a quick and dirty overview of getting around in open altimetry. Here's my
Okay, I think I think this is
if that you'd like mail, NSIDC@nsidc.org. We have more than just me. I'm the user services staff, but I'm the one who primarily answers either open altimetry or ICESAT-2 data questions. And we're more than happy to answer any questions you have. This is the link to some of the technical specs for the ICESAT-2 instrument. That's where you can see like the footprint diameter, the beam pattern, description, that sort of thing. And then this link.
Can I share again?
Oh, yeah. Yeah, okay. So I think I should this one. Yeah, yeah. So this one I actually don't need to share again here because yeah. So let me just open the other one. Okay. Kind of view. Short.
Okay. So here's maybe
yeah.
Questions.
Yeah. Okay. Okay, anyway, so I think we only few minutes left. What I'm going to do is in the afternoon, spend the first 30 minutes to really do the activity practical. So everybody open activity, and then we are focusing maybe conception area, and then we can find a track from the ocean to the land to see the elevation ocean and elevation land, and tree canopy and then stuff. So then you can really know how to use them. Then after that, then we will go to the Google Earth engine. So we will have 6 modules to go from today. Any questions so far for today before we go to lunch? Okay. Question? Everybody is clear?
So you mentioned that it's the other option, slide. What is it?
The slide rule.
That's an online.
That's
way
the
to
yeah, that's the cloud plan. Cloud plan. So but they don't have all of the data. They have some data. So you can check which data if interested in data or not. And then they can actually also respond to requests. So you say, okay, I would like to work on this area of the data, but the data looks like it's not there. Can you put it there? They can work with you and maybe put it there. So yeah. Okay.
Well, the equivalent of HDF. So and CBF for NASA is like we don't use it much. So HDF5 is it because mostly NASA data. They use HDF5, which is not a really friendly file. So CSV really is the option to get that.
So yeah, from the open activity, you can directly download as CSV.
Pero más darle es super bien HDF en sí, pero yo por ejemplo Python tiene el problema, R también tiene problemas para poder leer. Entonces, si se puede mejor, si no hay HDF, tiene que ser más universal, usar el separado por comando. Super. We just left the link for the Zoom meeting at the afternoon.
Yes, yeah. Okay, good. So we can see you in the afternoon.
Sí, a las 3 va a haber una pequeña introducción al Google Engine. ¿A las 12? Okay.
Cool. Okay.
So late.
Okay. Good. Okay. I was saying that's too late. Yeah. Okay. Cool. So starting afternoon, really we do lots of practical. Everybody will get 30 on your hand. You can use the computer here as long as you have a Google Earth engine. Google Earth, Google account. Google account, yeah. Google Gmail account.
Everyone has it.
Yeah. So then we'll log in, we'll use that, and I think it's lots of fun. We'll learn lots of stuff. Okay.
Bueno, vemos entonces a las 2. Con la parte introductoria y todo, entonces ya a meter la mano.
So 2 o'clock, right?
Yes. So Sophia's going to stop reading.
Okay.